Thanks to Papers We Love and everybody for coming out. This is really cool. And I gotta say, it's a little bit odd for me doing this sort of thing because I give plenty of talks about academic papers, usually ones that I write, and to audiences. Usually the audience features less pizza and beer and more academia. But so this is a really neat thing that has happened, that there's all these people who are really excited about hearing about academic computer science. So as an academic computer scientist, I think that's pretty cool. And I'm happy to get to be a part of that and to present this paper. So this paper is really a paper that I do love. So this paper is one that has made a big difference in the course of the research that I've done, and one that I actually basically wrote a whole paper that ultimately ended up being just me re-explaining to myself the contents of this paper and how I used the great things that Matthew developed in this paper to do some of my work. So, but this paper is called Composable and Compilable Macros, although most people in the Racket community refer to it as by the subtitle, which is You Want It When. And there's a variety of other papers with takeoffs on the subtitle, like You Want It Where, etc. And this paper is from the International Conference on Functional Programming 2002, so about 12 and a half years ago. So let me just start by giving a little background on the context in the research community when this paper was written. So this paper is all about what was then called PLT scheme, and is now called Racket. And PLT scheme came out of the scheme community where there was no module system. And similarly in other Lisp systems at the time, there were also, like Common Lisp, there was no module system. Most scheme systems used various versions of the Common Lisp approach where you loaded things differently, although usually scheme systems didn't have multiple namespaces. So that's the sort of state of scheme module systems then. And that's roughly where the Racket module system was as well, before this paper. Macros in scheme had been developed over a long history. The first this is about 40 years into the history of Lisp macros when this paper was written, and about 15 years into the history of hygienic macros. So the key pieces of hygienic macros that get used in this paper were about 10 years old at the time, but they weren't really as widely used even in the scheme community. They were still a sort of hard to use thing. And this is, of course, written in the context of Racket, or as it was then called, PLT scheme, and it was then a language that was primarily designed for building this IDE for teaching. Dr. Scheme, now Dr. Racket. And one of the key innovations there was that there were multiple language levels built into the IDE that you could switch between as you progressed in your programming education. And that idea really informs some of the key insights in this paper. So that's where this paper came from. And So when I sat down to work on this talk, I realized, well, hey, I know Matthew. Matthew saves everything that he's got. And we've done a pretty okay job with backwards compatibility in Racket. So I wonder if Matthew still has his slides. And so I sent him an email, and lo and behold, he did still have his slides, and not only that, but they ran first time. So these slides and Matthew's slides from 2002 are written in a program called Slideshow, which is a domain-specific language in Racket for writing presentations that Matthew is also the primary author of. And so that's what I use to write my slides for all my talks, and that's what this presentation is given in. And so I just ran it, and it worked. So I decided that what better way to present a paper that I really like than to present the original slides as they were designed by the author of that paper. So without further ado, here's Matthew's talk on composable and compilable macros. I feel like we progressed a little in the graphic design, and the fonts looked worse in the original version. Okay. So this is really the reason Matthew wrote Slideshow, is so that he could have these faces. There's a whole library of these faces. There's also a function in the Slideshow library called standard fish. It produces a picture of a fish. You can make the fish point left or right, or have its mouth open or closed, or have little bubbles coming out. There isn't a non-standard fish, though. So we have our happy scheme programmer who sadly is having to develop an Emacs. Fighting words, eh? And really sadly, they're still stuck on MISCHEME version 103. And they're developing some parser for some file format. And they've decided to use a language extension for writing parser generators. In fact, just such a language extension exists in Racket today. That's what's primarily used for writing parser generators. It's a system a lot like Lex and Yak. And you really do write things that look almost exactly like this 15 years later. Nothing new under the sun. And we're all very happy about this. But here's the problem. Load is not a very good module system. What load does is it just takes your file and it executes all of the things in that file. And then you're left with the state of the world after that's happened. And that's not so good, because it's very hard to compile programs in that setting. So if load of this Lex and Yak is going to define the Lex syntax extension, then when we go to try to compile this file to bytecode, so Racket then and now used an ahead of time bytecode compiler to do macro expansion and bytecode compilation. Then we're not, since load is a runtime sort of thing, we're not loading it at compile time. Therefore, we don't have any idea what Lex means. So we're sad. So the usual solution for this is, well, let's load it at compile time too. So this is a technique that comes from common Lisp, which is eval when. You say, okay, well, also, when we're going to compile this file, we need to load our syntax extension. And in fact, we only need to load it at compile time because it's a syntax extension, it's not runtime stuff. Well, that's what we think at any rate. So that's another problem. We can't take this from one compiler to another compiler, so we need to switch and add yet more eval when declarations. One other problem that I'll point out, even without this, is probably there's a bunch of definitions of runtime support for your parser generator. There's going to be stuff for reading in input characters and buffering and handling error messages and that sort of thing. And that's all going to need to run at runtime. So if we go back to our only compile time version of loading this, then at runtime, we're going to be out of luck because we don't have that. So now we need to load it at both runtime and compile time, but probably we discovered that by trying this and then deploying it on some other machine and then discovering that it didn't work after all. So that's no good. So the problem with load is that load is about side effecting the state of the world and scripting the compiler to insert these side effects at various points. So you can see that if we have this program here, we're loading a whole bunch of different things, and who knows exactly when all of these are going to happen. We've got this order and we have a lot of conditionals to control this. So you can see, however, that the blue arrows are not going to be the same as what the program really cares about. The programmer cares about these green arrows. That's why we have some library A that depends on the contents of U, or depends on the contents of M, and one file depends on the file that we loaded previously. But these are not represented by the purple arrows that we see. So we've already got a mismatch between our implementation and what we're trying to represent. So that means that we're not going to be able to change things and expect to have anything work. So we've got a compiled file, so we see that when we're in compile mode, we're only loading M. But if MA depends on, if we add a dependency from MA to U, then that's not reflected. That dependency is just, oh, I refer to this name in one place, and it happened to have been previously loaded. But it's not reflected in the program. And so this is going to fail when we try to compile the program ahead of time, but it will have worked just fine while we were developing the system. And so that's really the worst kind of bug to have, where it manifests only in some of your configurations, in particular, only in the configurations that you don't try as often. Definitely worse than the other way around. So now we fix this to add another load here, because these are all at the same level. Of course, we still haven't really fixed this because it's not in the correct place. So in addition to not being really fixed, when we load is just run some code. And that means we can run some code more than once. And if that code just consists of defining a bunch of names, maybe it'll work out. Okay. Snakes? think we were on a plane. So if we've just defined a bunch of functions in U, then probably we're okay. Well, maybe we're okay because now we've got two different versions of these functions and they're not going to be in Q and they're going to close over a slightly different state and you're going to eventually discover that this doesn't actually work. So that's no good. So we're continuing to have two problems. One is that we're not expressing what we really mean. We're not expressing these green arrows in the structure of our program. They're just sort of in our head. And the second problem is that we keep discovering that things are not loaded at the correct time. And of course, these are the same problem. That the solution to having things loaded at the correct time when you actually mean it is to express what you mean in the program. So the solution to this is to declare what we want, when we want it, and have it mean the same thing regardless of how you run your program. It should mean the same thing if you're compiling your program with an ahead-of-time compiler. It should mean the same thing if you're compiling it to an executable or to bytecode or compiling all the files at once or separately or loading the whole thing into an interactive REPL. And so that's what the solution that Matthew proposes here is going to do, and basically we've kept that solution in Racket ever since. So here's what it looks like. We have modules that look like this. We wrote left paren module back in 2002, and these days in Racket we would write hashline and save ourselves 2 characters of indentation and 2 parentheses. Precious parentheses. So we've got 2 definitions in this file. We've got a definition of a macro, and we've got a definition of a function. And it's important to keep track the different kinds of expressions that these definitions produce. So these green highlights, so clouds are another theme with slideshow presentations. There's a whole library of generating clouds. So these green clouds are runtime expressions. They're going to happen when we actually run the program. And these purple clouds, those are compile time expressions. They're part of our macros, that is our extensions to the compiler. And we're only going to need those to expand the program to turn it into a fully compiled program. And then we're going to be left with a bunch of green expressions to actually run our program in the end. So another important thing to note is that the purpose of a macro is to generate a program. And that program that you generate is going to be run at runtime. Well, at somebody's runtime. So when we write quote, this is actually called quote, this is the syntax quote form in Racket. It constructs a piece of syntax, and that's going to be running at runtime. So really we're going, when we quote things, when we construct syntax, we're going back from the meta level, the compile time program, back to the runtime program. So we escape back from purple into green by having in this purple cloud, little green cloud inside our little quotation. By the way, I'm happy to take questions if people have questions about any of this or about how they can acquire more clouds in their presentations. Yeah.
So are macros available at runtime?
I'm not 100% sure what you mean by that.
Well, the way you described it made it sound like there were compiler extensions that were only available at compile time. I assume Racket has a runtime requirement. Is the compiler available at runtime in Racket?
so there's a compile function and an eval function, and you can do that. But even in those situations, we're still going to distinguish purple from green here. We're still going to make a distinction between compiling a thing and then running them. So we'll get a little bit later to something that will answer your question a little bit more about how this is different from the way it works in more conventional Lisp systems. Any other questions? Okay. So now we see something important, which is our first import, which is we're going to require this A module into our B module. So we've got an import, and now we're going to be able to use M and F. And again, in B, we've also got some macros and some function definitions.
One module per file?
Roughly. I'll mention briefly why that's not really right at the end of the talk. So it's also important to note that this require statement is in green. So this is a runtime require. So we're going to be able to use the things that A defines at runtime. And again, we can distinguish green from purple in B as well. And these are the same green and purple that they are in A, because the runtime of A and the runtime of B are both going to be the real runtime of our program. However, we might want to use something more interesting inside our definition of this macro. The end macro might need some complicated library to implement it, because your macro might depend on a list library, or a hash table library, or a syntax error library, or who knows what. Or it might, your macros might download data schemas to generate things, or they might connect to your database to generate your ORM at compile time and that sort of thing. So what we're going to do there is we're going to require U for syntax. That is, we're going to say we want to use the things defined in the U module at purple time. And but note that up here, the thing we're defining in U is written in green. Fold here is written in green. So we can also, however, have an arrow where we use fold at runtime from A. So now let's think about where these colors go. So when is runtime for the U module going to happen? It's going to happen twice. It's going to happen twice because it's used both at the compile time for module B, and it's used at the runtime for module A, which is the same as the runtime for module B. So we have to have fold available both at compile time and at runtime. So if we think about, if you imagine that compile time happens on your compile server farm somewhere else several weeks prior to when you're actually running this program, it's easy to see that these have to be two different, really definite instantiations of this library. We have to have a version of fold over on the compile farm, and then we have to have a version of fold that's available to run when we're running on our deployed service. So we've really got to have this available at both different times. And that's getting back to our examples from the beginning, that's really what was going on with those eval when statements. We were saying that we needed U both at multiple times. But here, that just falls out naturally from how we've expressed the dependencies in the program. And the important thing here is that we're going to need 2 instances of fold, and we're always going to get 2 instances of fold. If we just loaded this whole thing up into the REPL, we could say, well, we already got 1 instance of fold, why make another one? And the answer is, if you don't make another one, then things are behaving differently between your scenario where you're compiling your program on your compiler farm and deploying it on EC2 versus the scenario when you're debugging it on your laptop and loading it all into the interactive environment. And situations in which your program behaves differently depending on how you've set up your development environment are really no fun. And so we're always going to have 2 instances of U for each of the, one for the purple phase and one for the green phase. Yeah.
So does that mean that if module U creates some local mutable state, that there are going to be 2 copies of that, one at compile time and one at runtime, that don't see each other?
Yes. And it's really mutable state where this is really important, because if we just create the same version of the fold function and shared that, that's probably not going to bother anybody. But it's when we create, when there's a difference between creating multiple files or creating only one file, or creating multiple hash tables and sharing them sometimes and having different mutable hash tables at a different time, that's when you get really confused and you can't figure out why your program works some of the time, it doesn't work others of the time, and it only works if you hit run right before your background watcher job compiles the file again. And that just, nobody wants that. Okay. So that's the basic structure of the solution. We're going to express our dependencies, and we're going to, in particular, express our dependencies for particular times, not just for particular names. We're not going to assume that everything is always available at every time. We're going to say we need this now, we need this later, we need this at compile time. And so turns out that this lends itself to some really interesting patterns for creating interesting abstractions with macros. And I'm going to walk through this example, and a bigger version of this example really happens in Racket whenever you do pattern matching on data structures. So imagine we have a little record definition form in our Racket program that's define record, and we can create zebras with stripes, and we can also create lizards, and we can pattern match on whether we have a zebra or a lizard. So far so good. And then what's going to happen is in this is going to be 2 different cases, and in this case we're going to bind W and S to the weight and the stripes of the zebra, and here we're going to bind W, L, and C to the weight, length of color of the lizard, and we're going to do the respective right-hand side. So this is a pretty simple language extension. So this is the results you get. So what happens if we try to use the wrong version of zebra? Say we assume that zebras have colors, but we're incorrect because zebras are always black and white. So this should be a syntax error. We should statically know how many fields there are in a zebra. We should statically know that we don't have to specify the color of a zebra. So that's something we want to know statically, and that means that that static information has to be communicated at compile time from the definition of the zebra record to this record switch statement. And not only that, But these blue lines that I've drawn here, those are module boundaries. So we're really doing a require from the module down here to the module up here. And we're going to say that you have to fetch the static information about zebras from the zebra module down into the weight computation module in order to get this syntax error. So let's see how this would work. So we've got a macro definition for defining records. We've got a macro definition for record switch, our pattern matching form. And our zoo module, which is going to define zebras, it's going to have a require that says we're going to use all of these things at runtime. So this is maybe a good place to point out one little subtle point about this, which is when you write a syntax definition, what's runtime and what's expansion time? So we use record switch and define record at runtime, but we implement them at compile time. So we can use define record with a regular require. This is runtime, this is green here. But the right-hand side, the implementation of this, that's going to be compile time code. So, so that's an important point that can be a little subtle because it's unlike functions where their implementation and their use are going to be at the same level. Okay, so here's basically some snippets from the implementation. We're going to define the name for zebra, which is going to construct records. We're going to have an ISA check to see if we've got a zebra and that sort of thing. And the expansion of define record is therefore going to expand into this construct a zebra. And the same for record switch. However, we can make things a little more interesting by moving some of the runtime support for our record system, the thing that lets us create new records, over into this runtime support module. And that points out that now we need some additional support from the macro system and the module system to know that when we expand to this use of make record and ISA, we have to be able to reference the RT module and reference it at the appropriate phase, even though this is sort of an indirect reference because we've got two requires to get there. But it's still all green, it's still all at the same phase, so this should all still be fine. So the other thing to note is that imagine we want to keep track of these names so that we can give that syntax error. We're going to do that by having a compile time table that says, here's how many fields zebras have, here's how many fields lizards have. And we're going to define that in this compile time module, which just has a table. It'll just be a hash table. And then we're going to load that at expansion time for the record module, which is again expansion time for the zoo module. So that means we're going to be able to use this table in the computation of what the answer is. So we can do things like check for syntax errors. And we're not just going to generate code that references this table. Instead, we're going to run code that uses the table at compile time. So what define record is going to do is it's going to, in this purple code, it's going to say, okay, update this table, add an entry for zebra. And then what our record switch form is going to do is it's going to say, okay, look in the table and check to see if zebra is there. And check to see if we have the right number of fields for zebra. So now we're happy. But now let's imagine what happens if we're using our zebra definition from another module. Now, remember that each time we load a module, we create a whole fresh new state. Each time we expand a module, we don't share those mutable hash tables. But right here is a mutable hash table whose whole point was to be shared. So now we're set. So if we didn't have a solution to this, we'd be sort of out of luck, and we'd be unable to write these kinds of programs. Fortunately, we have a trick here. Instead of manually updating the table inside the implementation of define record, we're going to generate code that updates the table. That's going to be put into the zoo module, and it's going to say at expansion time, whenever you load this module, even if you've already expanded the define record, run this little bit of code. And the little bit of code that's going to run is going to put zebra in the table. So every time we construct, every time we throw away the state, we're going to load the little bits of force syntax information in all of these modules, and we're going to recreate the correct state of the table.
How is the state persistent?
So the state's not persisted. So that's sort of what the trick is here, that instead of persisting the state, we're going to persist code that recreates the state. So every time we expand any module, when we expand the zoo module, we're going to generate code that updates the state.
And how is that code persistent?
Uh,
How is it computer?
So when we
Defining the defined record?
So the persisted code is the output of the defined record macro. So if we look up here, this defined record macro, it constructs code that is going to be in the expansion of defined record that is going to update that table.
So anybody that runs zoo will get zebra.
Yeah, exactly. So we're going to expand define record, and it's going to not just expand into the usual function definitions, but it's also going to expand into this little bit of extra code that anytime we load this module, it's going to update the table and say, hey, remember about zebras? They've got 2 fields.
So you're already persisting some data between phases, namely the syntax that you're generating. Could you also just at the end omit the entire table?
So syntax has the nice property that we know how to write it down to a file. When we create arbitrary program values, those can be really hard to write to files, closures, sockets, databases, that sort of thing. So that means that's one of the reasons why it's hard to have consistency in the eval-when style model between something that runs at compile time and something that runs at runtime, because it's easy to accidentally rely on some state that isn't serializable. And so it becomes hard to fix that problem because you develop the whole system with the assumption that you'd have this data there, and now you have to turn it into something that you can serialize. So here, you can't get away with thinking that you're going to serialize anything other than code. For things that serialize easily, you can serialize them as code that you just load up again. Strings, quoted data, that sort of thing. And that'll work fine. But and that works fine. You You don't have to write it as
So
definitions that mutate some table. You could just write it as definitions that have the serialized information.
So in a more modern racket environment where you have something like the transparent operation of defining your records or structs, whatever they call them, then you have more flexibility here.
Yeah, you have somewhat more flexibility in terms of what kind of data you can put in this table and you can serialize into the code. But you can always just write a program that constructs the data you want. Yeah.
So wait, is the problem is that we have this table and we want to preserve it between compile time when it's created and then also have the round at runtime. Is that the problem?
Not quite. The problem is that we want to have something that this defined record knows something at compile time, which is how many fields zebras have. And the way it records that to communicate between the defined record form and the record switch form is it uses this compile time table. And we want that to still work even when the defined record form and the record switch form are in different modules. But the problem then is that the expansion of zoo and the expansion of client get different copies of this CT module.
Why?
Because we always want to create fresh instances of our shared modules at each compile time. Otherwise, because again, if we do separate compilation of zoo and client, then we will of course have separate copies of the table. So therefore, it's important to always have separate copies of
So
the table.
the important bit here is that like I can have two compile times, not just because these are at different phases, but because I'm compiling this piece of my code base separately from this piece of my code base.
Yeah.
Okay.
There's lots of ways in which you can separate the compilation of two different pieces of code, and anytime it could be separated, it's really important to not sort of allow them to intermingle accidentally in the cases where they're maybe not separated, otherwise you get into trouble. Okay, so now the record expansion has the same old runtime stuff and this for syntax information that updates the table. And our programmer is happy. So this is, I think, one of two really crucial contributions in this paper. So the other contribution in this paper, Matthew spends about a paragraph on, which is that every module in Racket specifies what language it's written in. And in the paper, Matthew says something, the language is usually MZ scheme, Ms scheme. And that was true in 2002, but it's not true today. So that feature that we write this down, which seemed pretty redundant back then when we were already writing Ms scheme, that's a hugely powerful feature. As it says in the paper, it provides that initial import provides the initial meaning of all of the standard bindings, like plus, but also like define and lambda, and even the meaning of application, function application. And because we say that we're importing them from this thing we write down in the language, that means you can write down a different thing in the language, and then it can provide a different set of imports. And so that lets you build new languages and just switch which language you're programming in by changing that one thing that you wrote down at the top. And so you get the many different languages in Dr. Racket. So you can see the lovely 2002 vintage screenshots. We've got a bunch of different languages, like here it says languages beginning student, which was the language that Racket was started to be able to develop. And then we can also switch to a language in which we write slides with module, and we're referencing slideshow. And we're loading faces and balloons to get the appropriate graphics for this talk. And you can, these days, Dr. Racket actually says that this is written in the slideshow language, because that's really what's going on here. That every module defines its own language, and that's the language you're programming. And we also have a bunch of compilation modes that this system supports across all of them. There's just running the program, there's just expanding the program, which is obviously not going to run the green parts of your program, but it is going to run the purple parts of your program. There's another way where we're creating an executable, bundling everything together, and that's going to require you to specify where your dependencies on different runtime resources are going to be so that the compiler can find them all and bundle them into an executable. And that's something else that's supported by the macro and module system. So now we're all very happy, especially since we don't have to have 2002 vintage computers anymore. So that's the end of Matthew's talk. So we can all be thankful to Matthew, and I want to talk a little bit about what's happened since then. So the module system that I just presented is basically the module system that's in Racket today. Some of the details of the syntax are different. Turns out that you need to be able to talk about phases in the future as well as in your past, so that you can, if I'm generating a program that's going to be run at someone else's runtime, I have to say, this program lives in the future from me instead of in the past from me. So that's an important idea. This has become the basis for the module systems that have appeared in the R6RS and R7RS scheme standards, although maybe the less said about scheme standards, the better. And this design has influenced other module systems that have been designed since. It was a big influence on Dave Herman and myself when we were designing the JavaScript module system that's going to be in ES6, although really more in thinking about the kinds of ideas that, and the kinds of problems that Matthew set out to solve, thinking about deployment and customization of the language and that sort of thing. The macros, yeah.
So a question about the future and the past phases you were talking about. So future is just quote, right? You just move it forward.
Yeah.
And then so what's the opposite of that?
That's the being on the right-hand side of the defined syntax is at compilation time relative to where I am.
Gotcha.
And quoting goes back. So the reason that you need to be able to talk about things in the future from me is if you just have a regular module and you just write quote in it. What phase is that talking about? That's talking about one in the future from me instead of one in the past from me. You can now in Racket specify arbitrary numbers, but I've never written a number bigger than 2, so. So the macro system has also evolved in a lot of ways since 2002. We've developed a bunch of tools for writing better macros, like the syntax parse system and the macro stepper debugger, which are really valuable for understanding the complexity of the macro system. There's a lot more features that have been added to the macro system to make things easier. Turns out that there's better ways, for example, to do that record example than compile timetables. And the language feature that I talked about, that this paper discusses briefly, has really come into its own in Racket since then. And it's used for things like Typed Racket, for things like our documentation generation system called Scribble, which changes the syntax of the language, the concrete syntax of the language pretty radically. or even languages like Datalog, which are written in a very different syntax. Yeah, and so I did say that turns out this isn't the right way to do record syntax checking, but that table approach is exactly how Typed Racket works and how it communicates the types of functions from one module to the next, with basically that exact diagram, except with more numbers of modules. So I thought I'd end this with a few other fun papers to read that connect to this paper. So obviously, really? My PDF conversion has failed. And that's really too bad. So here are some papers that you should take a look at. Obviously, if you haven't read this paper, it's really great. It does an excellent job explaining the problem, the solution, and how to use the solution to get things done, which is one of the things that I really like about it. Matthew wrote a follow-on paper to this about 10 years later in 2013 at the GPCE conference called Submodules in Racket, and it's about the submodule feature, which answers the question I had earlier about whether there was more than one module per file. So now, in the last few years, Racket has grown this submodule feature, which turns out to be incredibly powerful for describing a lot of different aspects of your program in a sort of faceted way. So you can say, here's the main code of my module, and then here's the extra stuff that you should look at for my module if you're testing it. So you can write the test submodule, and then your unit test system loads that, and that loads your main module. Or you write the main submodule, and that's what you execute when you run that file on the command line, instead of the sort of testing whether your name is main or that sort of thing. Typed Racket makes heavy use of submodules to contain the type information about a module, and there's many other examples. So submodules really tie closely into all of the examples, all of the features being used here about phases and compile time state and name binding and languages. So another paper, to toot my own horn briefly, is our paper from PLDI 2011 with myself and Matthew and many other people about the implementation of Typed Racket. And it's called Languages as Libraries, and it really lays out how to take the technologies that Matthew presented in this paper and a number of others and turn them into a full-fledged new different language that does everything from new syntax to static checking to language interoperability with untyped Racket to an optimizing compiler, all built as a library using the facilities that Matthew described in this paper. And then one other paper is called Macros That Work Together, also by Matthew, Robbie Findler, and some other people, which is about the nitty-gritty details of how macro expansion works in Racket. Not addressing the module system at all, but really taking the other perspective and showing how the things that we wrote in those little green and purple bubbles, how they really work when we're trying to produce our new programs. And so those are 4 great papers. I think they're all ones that I listed that are up on the meetup page, and I encourage you to check them out if you found this paper fun, because they're all really great papers, maybe even including mine. So with that, I'm finished, and you are all a great audience, and this has been a pleasure.